Okay, so here we have another problem under the same topic, and we are given the same acid, it's boric acid with a given Ka. We also have a different pH in this second example problem. So our first step, again, is to identify the major species present in this solution. I'm going to move a little bit more quickly through this example, but I move more slowly in the first example under this topic, and I provide a little bit more explanation. So the major species present will be boric acid. Of course, we're going to omit water. We ignore the auto-ionization of water and how it contributes to the hydronium ion concentration because it's so small. So boric acid. The second major species will be hydronium. And again, this can be written as either H plus or H3O plus. And the third major species will be the conjugate base of boric acid, which is that, right? Well, once we have identified the major species and our acid dissociation reaction equation is balanced, then we build our ice table. To build our ice table, we have our initial, change, and equilibrium concentrations. Initial, change, and equilibrium. Well, the initial concentration of this substance right here, boric acid, well, it's given is 0.63 molar. Well, the initial concentration of this would be 0 and 0 initially. But we know that this reaction is going to go forward to some degree. It's also going to go the reverse, but it will reach and establish an equilibrium. So at equilibrium, these concentrations will not be 0, but initially they are. Well, what is the change in concentration represented as? Well, we're going to use X to represent the change in concentration, but we don't know how that concentration is going to change yet, but we're going to solve for X. So because we're starting with this concentration of boric acid, we know that at equilibrium, it's going to be something less than that, okay? So the change is going to be negative, minus X. The change for H plus is going to be plus X, and for the conjugate base is going to be plus X because these concentrations are going to increase. So what are the equilibrium concentrations here? Well, we treat this just like an addition problem. We're going to add these two together. When I add these together, I get 0.63 minus X. What's 0 plus X? Well, plus X. What's 0 plus X? Again, plus X. So what I have here are mathematical representations of what the equilibrium concentrations of each of these major species are at equilibrium. So at equilibrium, in this solution that is 0.63 molar boric acid, well, at equilibrium, the concentration of boric acid is going to be 0.63 minus X, whatever X is. At equilibrium, the concentration of hydronium is going to be X, and at equilibrium, the concentration of this conjugate base is going to be X. So what we have to do now is solve for X. So our first step in solving for X is to write the equilibrium expression for the ionization of boric acid. So that's going to be Ka, which is the acid ionization constant. It's equal to the concentration of H plus times the concentration of the conjugate base over the concentration of boric acid. And that came from this right here, okay? Now we're going to substitute Ka for its actual value. What is the actual value of Ka? It's given as 5.8 times 10 to the minus 10. So 5.8 times 10 to the minus 10 is equal to, what is the concentration of H plus or hydronium equal to at equilibrium? Remember, this is the equilibrium expression for the ionization of boric acid. But the equilibrium is the key word. So at equilibrium, the concentration of H plus is equal to X. And so that's what I'm going to plug in here for H plus. Well, let's look and see what the concentration of H2BO3 ion is at equilibrium. And it is X at equilibrium. So I'm going to put this times that over whatever the concentration of this is at equilibrium according to our ice table. Well, at equilibrium, the concentration of boric acid is 0.63 minus X. So that is what I'm going to put here. Okay? Now, before I move forward and go to solve for X, I have to try the approximation method to see if I can use it, because it'll make the math so much easier than having to use the quadratic formula to solve for X. And so to use the approximation method, I make this assumption. Because Ka is so small, this is the value, okay? I make the assumption that X will be so small that if I subtract X from 0.63, the answer I'll get would be pretty much 0.63. So I can make an approximation here. And the approximation that I'm going to make is that I'm not even going to bother subtracting X from 0.63 because it's so small that it really won't change anything. And so I end up with this. And so now I can solve for X by multiplying both sides by 0.63. And when I do that, I end up with X squared is equal to 3.654 times 10 to the negative 10. Then I take the square root of both sides, and I end up with X is equal to 1.912 times 10 to the negative 5. Now we can go ahead and test the approximation method right now before we move on. So how do we check the approximation method to see if it's valid? Well, I take my value for X, 1.912 times 10 to the minus 5, and I divide it by the initial concentration, which is 0.63, and I multiply it by 100 to convert it to a percentage. What I get is 0.0030%. So this is much less than 5%, which tells me that this approximation is valid and I can use this value for X. If it were greater than 5%, then that means that the approximation is not valid and I cannot use it, and I have to use the quadratic formula to solve for X, so I need to keep this here. I could not just omit it like we did there. So now that I know this change in concentration or value from X is valid, let's plug it in and solve for our equilibrium concentrations for each of these three, 1, 2, 3 major species. So we have boric acid, we have hydronium, and we have the conjugate base. What is the concentration of boric acid equal to at equilibrium according to our ice table? 0.63 minus X. This one is equal to X, and that is equal to X. So let's take X and plug it in there. This would be equal to 0.63 minus our value for X, which is 1.912 times 10 to the minus 5. 1.912 times 10 to the minus 5. This is equal to 1.912 times 10 to the minus 5. And this is equal to 1.912 times 10 to the minus 5. So this concentration for boric acid would be 0.63. And you can see, of course, well, that falls in line with the approximation that we made. We said, well, x would be so small that if I did subtract it from 0.63, it'd be pretty much 0.63, which is what we did here, and we ended up still with a value that rounded up to 0.63. So now that I have the equilibrium concentration of hydronium, I did get equilibrium concentrations for the other species, but this is the one I need to find the pH, because pH is equal to the negative log of the hydronium ion concentration. So pH is equal to the negative log of the hydronium ion concentration, which is 1.912 times 10 to the minus 5. That would give me a pH of 4.7 rounded to 1 decimal place.